from Math Magicians, and we will continue with our course of physics. As promised in the last video, the answers are going to be published here. Now, we will continue talking about measurements in experiments. Physicists perform experiments to test the hypothesis about how changing one variable in a situation affects another variable. An accurate analysis of such experiments requires numerical measurements, which, as you can see, is our subtitle here, numbers as measurements. The SI unit is the standard measurement system for science. SI in English means International System of Units. In SI, there are only 7 base units, and each base unit describes as a single unit, such as length, mass, and time. The base unit for length, mass, and time are the meters that we abbreviated for with an M. The mass is the kilograms abbreviated with a kg, and the time that is abbreviated with s of seconds. With this, we continue with the next part of the video. Now, physics is a science that describes a broad range of topics and requires a wide range of measurements, from very large to very small. This is why in physics we combine our SI units with certain powers of 10, such as or shown in this figure. In this figure, we can say that, for example, 1 millimeter is equal to 1.0 times 10 to the 3 negative meters. We can also say that 1 kilometer is equal to 1.0 times 10 to the 3, let's fix that 3, meters. Okay, so this table helps us to make a conversion. As you can see, both dimensions and units must agree. That is why we use the equality sign. This takes us to the next part. The next part is an exercise or a word problem. It says, if a statue has a mass of 60 million milligrams, what is the mass in grams and what is the mass in kilograms? So let's start by defining how many milligrams are in one gram, or how many grams are in a milligram. That's up to you how you want to work with it. I have that 1 milligram is equal to 1.0 times 10 to the negative 3 grams. And if I have 60 million milligrams, I will copy it here with another color. 60 million milligrams. And I want to make a conversion. What I do is that I make a quotient bar. Okay, in other words, dividing. So I copy the same SI unit I have in my denominator so that I can cancel it, 1 milligram, and then I copy what is equal to. Is equal to 1.0 times 10 to the negative 3 grams. Okay, this indicates that I can simplify my milligrams, and then I just make my multiplication of 60 million with 1.0 times 10 to the negative 3. If you make your multiplication using your calculator, you'll have the answer of 60,000 grams. Okay, so that will be the answer in grams. Now that we have our grams, it's easier to find your kilograms. For that, I'll erase this and we will make the conversion now to kilograms. Okay, we know that is 60,000 grams. So we had 60,000 grams. Now, the conversion of 1 kilogram is equal to 1.0 times 10 to the 3 grams. So this is our conversion. We copy with another color the 60,000 grams. And we know already that in our denominator we have to locate the grams. That in this case is 1.0 times 10 to the 3. And in our numerator we locate our kilograms, 1 kilogram. So we cancel grams and we make this operation. This operation is dividing. 60,000 divided by 1.0 times 10 to the 3 in your calculator will give you 60 kilograms as an answer. And there you have your two conversions. Now we will continue with our next slide. The next slide is another exercise, and it says, if, let's change this. I'll try to move this. Okay, there we go. If a radio wave has a period of 1 mu s, mu is a Greek letter, okay? It stands for micro. What is the wave's period in seconds? We have to find the micro, in this case, microseconds. So we have that 1 microsecond, 1 mu s, is equal to 1.0 times 10 to the negative 6 seconds. Okay? And because it's your base, is what you're looking for. We're looking for to conversion of seconds. This is your answer. 1.0 times 10 to the negative 6. With this, we'll continue with the next slide. Okay, continuing. Now we're going to continue with accuracy and precision. Accuracy, as it says here, is a description of how close a measurement is to the correct or accepted value of the quantity measured. Precision is the degree of exactness of a measurement, and significant figures will help us to find accurate and precise answers. For example, it says significant figures, those digits in a measurement that are known with certainty plus the first digit that is uncertain. Because no measurement is perfect, we must consider both accuracy and precision. Accuracy, which describes how close the measurement is, and precision, which describes how exact the measurement is. Now, here we have an analysis to make. Error in experiments must be minimized. Okay, how do we minimize errors in experiments? The way we start measuring an object, or the way we measure a figure. For example, the way that you see the object is a way to minimize an error. For example, here we have a measurement of a borderline of a wall, and as you can see, the first one is the correct way to see it, but the second one takes away your precision and accuracy. With this, we continue with our next slide. The next slide is precision describes the limitations of the measuring instruments. Precision describes how exact a measurement is, okay, as we said in the last slide. Estimation is not guessing a number. Estimation means using prior experience and physical reasoning to arrive to a rough idea of a quantity value, as seen here. What you see here is that you can make an estimation because you already had a rough idea of what is a centimeter or what is an inch. Let's continue with the next part of the video. Now, significant figures, we already defined them in the last slides. Significant figures help keep track of imprecision, very important, and significant figures in calculations require special rules. Okay, the rules, we're going to see them right now. Right now, we're going to see the rules for zeros. Okay, when are zeros significant and where are zeros not significant? Number 1 says, 0 between other non-zero digits are significant. As you can see, you have 2 examples here. Another example can be, for example, let's write it here, 10.1. Okay, as you can see, you have a 0 between other non-zero digits, indicating that you have 3 significant figures. Number 2 says zeros in front of non-zero digits are not significant. You have 2 examples, as you can see there. Or you can say 0.92, for example. How many significant figures do I have there? I have 2, because the 0 in front of them is not significant. Number 3, zeros that are at the end of a number and also to the right of a decimal are significant. You have 2 examples here. Another example can be 47.00. How many significant figures do we have? We have 4. Number 4 is a tricky one. Number 4 says, zeros at the end of a number but to the left of the decimal are significant if they have been measured or are the first estimated digit. Otherwise, they are not significant. Okay, an example can be, let's say we have 2,000. Okay, 2,000 may have 1 significant figure or it may have 4 significant figures. Okay, they may have 1 or 4. Okay, that is depending on the precision of the measurement. I like to use scientific notations when I have these type of problems. Okay, I'll continue with the next slide. Rules for calculating significant figures. Okay, when you add, subtract, multiply, or divide. The addition. Given that addition and subtraction take place in columns, round the final answer to the first column from the left containing an estimated digit. You have an example here. I'll make another one. It says, for example, 85.3. And we know that we add them in columns, and we put the decimal over the decimal to make the addition. And if we add this, I'm going to change my color. I have to be careful with this column here. Okay, this column will tell me if I have to round up or round down. If I make my addition, I have 5. 9 plus 3 would be 12. I carry a 1. 5 plus 4 is 9, plus 1 is 10. I carry a 1. 8 plus 1 is 9. We have our decimal here. Now, remember this column. If this number is 5 or greater, you're going to round up. That means that this will be 90.3. Later on, we will see that there is another rule that tells if we round up or round down when it's even or odd. Okay, so that explains addition and subtraction. Now, multiplication or division. The final answer has the same number of significant figures as the measurement having the smallest number of significant figures. You have an example here that they have the same amount of significant figures. I'll make another one that has a different amount. Let's say, for example, 12.3 times 1.1. If we start multiplying, we will have 3, 2, 1, 3, 2, 1. We know that we add them. It's just a normal multiplication. We have 2 decimals. Will be here. So we have 13.53. Now, I have to round, let's say I want to round these to 2 significant figures. Okay, so my answer is 13.53, and I want to round it to 2 significant figures. I am going to choose the number that has the least amount of significant figures. That's why I chose 2. I'm going to choose the number that has the least number of significant figures, in this case 2. So I have to round this to 14. Why to 14? Because this 5 and it rounds up. Okay? So with that, we're going to continue with our next slide. Calculators do not pay attention to significant figures. You can use a calculator, but remember that you have to be careful with all these rules in physics. So, rules for rounding up or down, okay? Whenever the digit following the last significant figure is 0, 1, 2, 3, or 4, we already know this, that we round down, okay? We have an example, 30.24 becomes 30.2. We round down because the number is less than 5, okay? The next one, if the last significant figure is an even number, very important, and the next digit is a 5, with no other non-zero digits, we round down. Okay, you have 2 examples there. How you round down. I have another example here. Let's say we have, let's write a number, 42.853. And I want to round to 3 significant figures. As you can see, this number is even. That means that I have to round down to 42.8. Okay, now, when do we round up? Okay, I'll start by explaining this one because it's just the inverse of this one. It says that if the last significant figure is an odd number and the next digit is a 5 with no other non-zero digit, okay? So, if you have, for example, 17.75, okay? Now, this number now is odd. It's odd. And because it's odd, I can round up. If I want 3 significant figures, I can say that this is 17.8. And the first 2 rules, I'll change my color. This one here says whenever the digit following the last significant figure is 6, 7, 8, or 9, that is greater than 5, we round up. Okay, you have an example there. You round up. If the digit following the last significant figure is 5, followed by a non-zero digit, you also round up. And you have your example here. 54.7511 becomes 54.8. Remember that this number has to be an odd number. Okay, with that, we continue with the video. Now, these are some section assessments for you to practice. Thank you for watching, and remember, physics is life.